Hello there and welcome to the Sleepy Science Channel. Tonight we'll be descending into the vast and mysterious realm of the deep ocean, a place filled with silence, with wonder and endless secrets. Below the surface lie the usual sights: coral reefs, schools of fish, and the shallow waters we're all familiar with. But there is so much more than meets the eye. Some creatures glow with their own light in perpetual darkness. A simple current may carry nutrients across thousands of miles, and the soft drift of marine snow may contain the remains of life from the surface world. The deep ocean is both alien and familiar, something that covers most of our planet yet remains largely unexplored. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here too. One sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the calm of the deep ocean to carry you. Let's begin. When you look at Earth from space, blue dominates the view. The ocean stretches across more than 70% of our planet's surface, a vast liquid blanket that shapes climate, weather, and life itself. Yet, despite this enormous presence, we know less about the ocean floor than we do about the surface of Mars. Mountains taller than Everest rise from the seabed. Canyons deeper than the Grand Canyon carve through ancient rock. And across these hidden landscapes, life thrives in forms we're only beginning to understand. The ocean is not one place but many. From sunlit shallows to midnight depths, each layer a world unto itself. To understand Earth is to understand the ocean, for they are inseparable, woven together since the planet first cooled and water began to gather in its lowest places. Sunlight penetrates only the uppermost layers of the sea. Within the first 200 meters, light fades from bright blue to dim twilight. Beyond 600 meters, darkness becomes absolute and eternal. No ray of sunlight has ever reached the deepest trenches, places that have remained in blackness since the ocean formed. Yet this darkness is not empty. Creatures have adapted in extraordinary ways, developing their own sources of light, heightened senses, and strategies for survival that seem almost supernatural. The Midnight Zone, as it's called, is the largest habitat on Earth, comprising more than 90% of the ocean's volume. To descend into these depths is to enter a world where light is not given but created, where silence reigns, and where the very concept of day and night loses all meaning. In the western Pacific Ocean lies a chasm so deep it could swallow Mount Everest entirely with room to spare. The Mariana Trench descends nearly 11 kilometers below the surface, a place where the ocean floor itself bends downward under immense geological forces. At its deepest point, called Challenger Deep, the pressure is more than 1,000 times greater than at sea level. Every square inch bears the weight of nearly 8 tons. Only a handful of humans have ever visited this alien realm, and each journey revealed new mysteries. Strange pale creatures, ghostly and delicate despite the crushing environment. Microbes thriving in conditions that would destroy most life, and a haunting silence broken only by the faint sounds of geological movements far below. The trench reminds us that Earth still holds places beyond our easy reach, frontier territories within our own world. As you descend into the ocean, the weight of water above you grows with each meter. For every 10 meters of depth, the pressure increases by roughly 1 atmosphere, the equivalent of the air pressure we experience at sea level. At 100 meters, the pressure is 10 times greater. At 1,000 meters, it's 100 times greater. This crushing force shapes everything in the deep ocean. Creatures that live there have adapted bodies without air pockets, flexible structures that won't collapse. Submarines must be built with thick walls of reinforced steel or titanium to withstand the relentless squeeze. Even sound travels differently under such pressure, moving faster and farther than it does near the surface. For humans, unprotected descent beyond a few dozen meters would be fatal. Yet for the organisms born into this environment, the pressure is simply normal, as natural as the air we breathe above. Beneath the waves, hidden from sight, lies the longest mountain range on Earth. The mid-ocean ridge system winds through all the major ocean basins, stretching more than 65,000 kilometers. That's longer than the Andes, Rockies, and Himalayas combined. These underwater mountains form where tectonic plates pull apart, allowing magma to rise and create new seafloor. Along the ridges, volcanic activity builds peaks and valleys, some reaching heights that would rival the tallest mountains on land if measured from base to summit. Hydrothermal vents cluster along these ranges, spewing superheated water rich in minerals. Around them, ecosystems thrive in complete darkness, sustained not by sunlight but by chemical energy. The mid-ocean ridges are Earth's most active geological features, constantly reshaping the planet's surface in slow motion, far below where any human eye can easily see. Deep along the mid-ocean ridges, cracks in the seafloor release water that has been heated by magma far below. These hydrothermal vents can discharge water at temperatures exceeding 400 degrees Celsius, hot enough to melt lead. Yet the extreme pressure at those depths prevents the water from boiling. Instead, it shoots upward in black or white plumes, laden with minerals like sulfur, iron, and copper. As the superheated water meets the cold ocean, these minerals precipitate out, building towering chimneys of rock that grow taller over time. Some rise tens of meters above the seafloor, resembling alien smokestacks. The vents create oases of warmth and energy in the cold, dark depths. Around them, life clusters in astonishing abundance, fed not by the sun but by the chemical reactions between vent fluids and seawater. These vents are windows into Earth's interior, places where the planet's molten heart reaches outward into the ocean. For most of Earth's history, scientists believed all life ultimately depended on sunlight. Plants capture solar energy, herbivores eat plants, and carnivores eat herbivores. But hydrothermal vents shattered that assumption. Around these underwater chimneys, entire ecosystems flourish in total darkness, powered instead by chemosynthesis. Bacteria consume chemicals like hydrogen sulfide from the vents and convert them into energy. These bacteria form the base of the food chain, just as plants do on land. Giant tube worms, some reaching lengths of 2 meters, host these bacteria in their bodies, living in symbiosis. Eyeless shrimp cluster by the thousands, their bodies adapted to sense heat and chemical gradients. Pale crabs, ghostly fish, and other creatures gather in the warmth, forming communities that would be impossible anywhere else. The discovery of vent life in the late 1970s revolutionized our understanding of biology. It proved that life could exist independent of the sun, opening up possibilities for life on other worlds, in places once thought too hostile to support it. If you could descend into the deep ocean and watch carefully, you would see something falling. Tiny particles drift downward in an endless, gentle cascade. This is marine snow, a mix of dead plankton, fecal matter, mucus, dust, and organic debris from the surface world. Each flake is small, almost invisible, but collectively they form a constant shower that feeds the deep. For creatures living in the midnight zone, marine snow is essential. It carries nutrients from the sunlit surface down to the lightless depths, sustaining food webs that could not otherwise exist. Some animals filter it from the water. Others wait on the seafloor, consuming what settles. The journey of a single particle can take weeks or even months, drifting slowly through the water column, passing through different zones and ecosystems before finally reaching the abyssal plain. Marine snow is the ocean's way of recycling, a connection between the surface and the abyss, ensuring that nothing is wasted. In the darkness of the deep ocean, many creatures have learned to make their own light. Bioluminescence is the ability to produce light through chemical reactions within the body. Some use it to attract prey, dangling glowing lures in front of their mouths. Others flash patterns to communicate with potential mates. Still others emit clouds of luminous mucus to confuse predators and escape into the dark. The light is usually blue or green, colors that travel farthest in seawater. To witness bioluminescence in the deep is to see living constellations, points of light flickering on and off like stars scattered through the blackness. Jellyfish pulse with ghostly glows. Squid illuminate their bodies in shifting patterns. Even some fish carry light-producing bacteria in special organs, maintaining them like tiny lanterns. In a world without sunlight, these creatures have become their own stars, filling the void with soft, eerie illumination. One of the most iconic deep-sea predators is the anglerfish, a creature that looks almost mythical with its enormous mouth and needle-like teeth. Female anglerfish carry a specialized spine that extends from their heads like a fishing rod, tipped with a glowing lure. This lure contains bioluminescent bacteria that emit a steady light. In the pitch-black depths, this glow is irresistible to smaller fish searching for food. When prey swims close enough to investigate, the anglerfish strikes with shocking speed, its huge jaws engulfing the victim whole. The anglerfish itself is often small, just a few inches to a foot in length, though some species grow larger. Males are typically much smaller than females, and in some species, They permanently attach to the female's body, fusing with her and living as a parasitic mate. The anglerfish embodies the strange adaptations required to survive in a world of eternal night, where every advantage matters and light itself becomes a weapon. For centuries, sailors told stories of enormous sea monsters lurking in the deep. These tales were often dismissed as myth until scientists began finding evidence of giant squid. These creatures can reach lengths of 12 to 13 meters, with tentacles stretching far beyond their bodies. Their eyes are the size of dinner plates, the largest of any animal, adapted to capture even the faintest traces of light in the dark ocean. Giant squid are elusive, rarely seen alive, and much of what we know comes from carcasses washed ashore or caught in fishing nets. In recent decades, researchers have captured footage of living giant squid in their natural habitat, revealing creatures both graceful and alien. They move through the water with jet propulsion, hunt with powerful tentacles lined with sucker discs ringed by sharp teeth, and remain one of the ocean's most mysterious residents. Somewhere in the depths, even larger species may still await discovery. If the giant squid inspires awe, the colossal squid takes that feeling further. Heavier and bulkier than its giant cousin, the colossal squid can weigh up to 700 kilograms or more. Its tentacles are equipped not just with suckers, but with rotating hooks, making it a formidable predator. Very few specimens have ever been found, and no one has yet filmed a living colossal squid in the wild. What we know comes from a handful of dead individuals, often discovered in the stomachs of sperm whales, their primary predators. These squid inhabit the cold, deep waters around Antarctica, far from human observation. To imagine them hunting in the abyss is to confront the reality that Earth still harbors giants, creatures of immense size and power that move unseen through a world we can barely reach. They are living mysteries, proof that the ocean holds secrets still waiting to be revealed. Among the ocean's many remarkable inhabitants, sperm whales stand out for their sheer diving ability. These massive creatures can descend to depths of over 2,000 meters, holding their breath for up to 90 minutes. They hunt in the darkness, using echolocation to find prey like giant squid. Their clicks are among the loudest sounds produced by any animal, powerful enough to stun prey and navigate the pitch-black waters. A sperm whale's body is perfectly adapted for these extreme dives. Their ribs are flexible, allowing their lungs to collapse under pressure without injury. Their blood and muscles store extraordinary amounts of oxygen, and they possess special adaptations to avoid decompression sickness that would be fatal to humans. To picture a sperm whale gliding silently through the abyss, a 50-ton animal navigating by sound alone, is to understand the ocean's scale and the incredible ways life adapts to even the most extreme environments. Sound travels exceptionally well in water, much farther than it does in air. Whales have evolved to use this to their advantage, producing songs and calls that can resonate across entire ocean basins. Humpback whales are famous for their complex songs, long sequences of moans, cries, and whistles that can last for hours. These songs are thought to play roles in mating, navigation, and communication. Blue whales produce calls at frequencies so low that humans can barely hear them, yet these infrasonic songs can travel thousands of kilometers. In the quiet of the deep ocean, whale songs become highways of sound, connecting individuals separated by vast distances. Researchers have recorded these calls and mapped their patterns, revealing an acoustic landscape invisible to the human ear. The ocean is not silent. It hums with the voices of giants, a chorus that has echoed through the depths for millions of years. Below 6,000 meters, the ocean enters what scientists call the hadal zone, named after Hades, the ancient Greek underworld. This is the realm of the deepest trenches, where the seafloor plunges into chasms darker and more remote than anywhere else on Earth. Fewer humans have visited the hadal zone than have walked on the moon. The pressure is unimaginable, the darkness absolute, and the cold unrelenting. Yet life persists even here. Amphipods, small shrimp-like creatures, scuttle across the seabed. Snailfish, pale and gelatinous, swim through the water with surprising grace. Microbes thrive in the sediment, metabolizing chemicals and organic matter that drifts down from above. The hadal zone challenges every assumption about the limits of life. It is a place of extremes where survival seems impossible, yet existence endures, quiet and resilient in the deepest shadows. In the deep ocean, food is scarce. Marine snow drifts down in limited quantities, and prey can be rare, Many deep-sea fish have adapted by slowing their metabolisms to conserve energy. They move little, drifting through the water or lying motionless on the seafloor for long periods. Their bodies are often soft and gelatinous, requiring less energy to maintain than muscular active forms. Some have enormous mouths relative to their body size, allowing them to swallow prey larger than themselves when the opportunity arises. These creatures exist in a state of perpetual waiting, conserving every calorie, patient in a way that seems almost meditative. Life in the deep is not about speed or aggression. It is about endurance, efficiency, and the ability to survive on almost nothing for as long as necessary. In this way, the deep ocean teaches a kind of minimalism, where less is not just enough but essential. Despite its ominous name, the vampire squid is a gentle creature of the deep. It does not suck blood or hunt large prey. Instead, it feeds on marine snow, using sticky filaments to collect organic particles drifting through the water. Its body is covered in light-producing organs called photophores, which it can flash in patterns to startle predators. When threatened, it pulls its webbed arms over its head, turning itself inside out to reveal rows of fleshy spines, a defensive display that makes it appear larger and less appetizing. The vampire squid lives in the oxygen minimum zone, a layer of water with so little dissolved oxygen that few other creatures can survive there. This adaptation allows it to avoid many predators, existing in a niche others cannot tolerate. It is a living fossil, an ancient lineage that has changed little over millions of years, a quiet survivor in the ocean's least hospitable layers. One of the strangest creatures in the ocean is the barreli fish, a small deep-sea dweller with a completely transparent head. Inside this clear dome, you can see its tubular eyes which point upward, scanning the water above for the silhouettes of prey against the faint light filtering down from the surface. The eyes are extremely sensitive, able to detect even the dimmest glow. For a long time, scientists were puzzled by this fish's anatomy, unsure how it could see forward while its eyes pointed up. Eventually, research revealed that the barreli can rotate its eyes within its transparent skull, allowing it to look in different directions. This bizarre adaptation is perfectly suited to life in the twilight zone, where light is scarce and the ability to detect prey or predators from any angle can mean the difference between survival and starvation. The barreli is a reminder that evolution creates solutions we could never anticipate. Forms so strange, they seem designed by imagination rather than necessity. Most bioluminescence in the ocean glows blue or green, but a few species produce red light. This is particularly useful because most deep-sea creatures cannot see red wavelengths. Their eyes are adapted to detect blue and green, the colors that penetrate deepest into the water. By producing red light, these animals can essentially create their own invisible flashlight. They can illuminate prey without the prey knowing it's being watched. Dragonfish are among the most notable users of this strategy. They have red photophores beneath their eyes, casting a crimson glow onto the surrounding water. To them, the world lights up. To their prey, the darkness remains unbroken. It is a predatory advantage as elegant as it is effective, a hidden spectrum of light turned into a tool for hunting. In the deep ocean, where visibility is everything, the ability to see without being seen is a profound evolutionary triumph. In certain parts of the deep ocean, pockets of extremely salty water collect in depressions on the seafloor, forming underwater lakes and rivers. These brine pools are denser than the surrounding seawater, so they do not mix. Instead, they remain separate, creating distinct boundaries that look almost like shorelines. The salinity in these pools can be many times greater than normal seawater, making them toxic to most marine life. Creatures that swim into them often die almost instantly, their bodies preserved in the dense brine. Yet around the edges of these pools, specialized bacteria and other organisms thrive, feeding on the chemicals that seep from the seafloor. These brine pools are eerie, otherworldly features, places where you could technically drown underwater by entering a liquid denser and more hostile than the ocean around it. They are geological curiosities, remnants of ancient salt deposits dissolved and trapped in the deep. While hydrothermal vents are dramatic and energetic, cold seeps are their quieter cousins. These features occur where methane and other hydrocarbons slowly leak from the seafloor, often in areas with oil and gas deposits below. The methane does not erupt violently, but instead bubbles up gently, sometimes over thousands of years. Specialized bacteria consume the methane, converting it into energy through a process similar to what happens at hydrothermal vents. Around cold seeps, unique ecosystems develop. Tube worms, clams, and mussels cluster in dense colonies, all hosting symbiotic bacteria. The seeps also create carbonate rocks, formed by chemical reactions between methane and seawater, which build up over time into structures resembling underwater reefs. Cold seeps are windows into deep subsurface processes, places where the chemistry of the planet's interior mixes with the ocean, creating habitats that blur the line between geology and biology. Beneath the water, the ocean floor is not solid rock, but a thick blanket of sediment. Over millions of years, particles have settled, layer upon layer, forming deposits that can be several kilometers deep in places. This sediment is a mix of many things: clay minerals eroded from continents, the shells of tiny plankton, volcanic ash, and even cosmic dust from meteorites. Each layer represents a slice of time, a record of Earth's history written in microscopic detail. Scientists drill cores from these sediments to study climate changes, volcanic eruptions, and shifts in ocean chemistry stretching back millions of years. The sediment is also home to countless microbes, living in the spaces between particles, surviving on minimal energy in conditions that seem lifeless. The seafloor is not static. It is an archive, a graveyard, and a living laboratory all at once. The microbes buried deep in ocean sediments exist in a state almost beyond comprehension. Some are thousands of meters below the seafloor, where temperatures rise and pressure increases. They live in complete darkness, with no access to fresh nutrients. Their metabolisms are so slow that a single cell division might take centuries. These organisms are not dormant. They are alive, just operating on a timescale so stretched that it challenges our very definition of life. They survive by extracting tiny amounts of energy from chemical reactions in the surrounding rock and sediment. Some may be millions of years old, individual cells that have persisted through ages. Their existence suggests that life can endure almost anywhere, given enough time and the right conditions. They are the ultimate survivors, patient beyond measure, thriving in a realm where time itself moves differently. When a whale dies and sinks to the ocean floor, it brings with it an extraordinary gift. A whalefall is a feast for the deep sea, providing more food at once than many creatures will encounter in their entire lives. Scavengers arrive first, hagfish and sharks tearing into the flesh. Over weeks and months, the carcass is stripped, but the bounty is far from over. Bones contain oils and fats that seep out slowly, sustaining specialized worms and bacteria for years, even decades. Eventually, the bones themselves become habitats, colonized by organisms that break down the last traces of organic matter. A single whalefall can support a complex ecosystem for up to a century, creating a localized explosion of life in an otherwise barren landscape. These falls are also thought to act as stepping stones, allowing deep-sea species to spread across the ocean floor by moving from one carcass to another over generations. Between 200 and 1,000 meters below the surface lies the mesopelagic zone, often called the twilight zone. This dimly lit layer is home to more fish biomass than all other ocean zones combined. Billions of small fish, squid, and crustaceans inhabit this space, migrating vertically each day in what is the largest animal migration on Earth. At night, they rise toward the surface to feed on plankton. Before dawn, they descend back into the safety of deeper waters, avoiding predators. This daily journey, called diel vertical migration, plays a crucial role in ocean ecosystems. It transports carbon and nutrients from the surface to the deep, helping regulate the ocean's chemistry and the planet's climate. The twilight zone is also largely unexplored, and scientists believe many species there remain undiscovered. It is a vast living layer of the ocean, teeming with life we're only beginning to understand. The ocean is not just a body of water. It is the planet's thermostat, absorbing and redistributing heat from the sun. Warm currents carry tropical warmth toward the poles. Cold currents bring nutrients and cooler temperatures toward the equator. This constant circulation drives weather patterns, influences rainfall, and moderates temperatures across the globe. The ocean also absorbs vast amounts of carbon dioxide from the atmosphere, acting as a buffer against climate change. Without it, Earth would be far hotter and less hospitable. But the ocean's capacity is not infinite. As it warms and acidifies from absorbing excess carbon, ecosystems suffer. Coral reefs bleach, fish populations shift, ice melts. The ocean's health is intimately tied to our own, and understanding its rhythms is essential to understanding the future of the planet. Coral reefs are among the most vibrant ecosystems on Earth, yet they are constructed by creatures no larger than your fingernail. Coral polyps are tiny animals related to jellyfish. They secrete calcium carbonate, forming hard skeletons that build up over time. Generation after generation, these skeletons accumulate, creating the massive structures we see today. Some reefs have been growing for thousands of years, their foundations laid long before recorded history. Reefs support incredible biodiversity, providing shelter, food, and breeding grounds for countless species. They are sometimes called the rainforests of the sea, yet despite their importance, they are fragile. Rising temperatures, pollution, and ocean acidification threaten reefs worldwide. When corals die, the entire ecosystem collapses. Protecting reefs is not just about preserving beauty. It is about maintaining the health of the ocean itself. Off the coast of Australia stretches the largest living structure on Earth. The Great Barrier Reef spans over 2,300 kilometers, a mosaic of coral islands and shallow seas. It is so vast that astronauts can see it from orbit, a pale ribbon of blue and green against the darker ocean. Thousands of species call the reef home, from tiny clownfish to enormous manta rays. It is a place of color and movement, a thriving testament to the power of small organisms working together over immense spans of time. But the reef is under threat. Warming waters have caused widespread coral bleaching, and pollution from the land degrades water quality. Efforts to protect and restore the reef are ongoing, but its future remains uncertain. To lose it would be to lose not just a natural wonder, but a critical piece of Earth's ecological fabric. Not all underwater forests are made of coral. In colder waters, giant kelp creates towering forests that rival those on land. These algae can grow up to 60 meters tall, rising from the seafloor toward the sunlight above. Kelp forests are fast-growing, sometimes adding half a meter in a single day. They provide habitat for fish, seals, otters, and countless invertebrates. Sea otters in particular play a crucial role in kelp ecosystems. They feed on sea urchins, which would otherwise devour the kelp. Without otters, urchins multiply unchecked, turning lush forests into barren underwater deserts called urchin barrens. Kelp forests are dynamic, constantly growing, dying, and regenerating. They are places of beauty and productivity, where light filters down through swaying fronds and life thrives in the cool, nutrient-rich water. Sea otters are among the few marine mammals known to use tools. They often carry a favorite rock tucked into a fold of skin under their arm. When they catch a shellfish or sea urchin, they float on their backs, place the rock on their chest, and smash the shell against it until it cracks open. This behavior is learned, passed from mothers to pups, making it a form of culture. Sea otters are also remarkably dense in fur, with up to 1 million hairs per square inch, the thickest coat of any mammal. Unlike seals and whales, they lack blubber for insulation, relying entirely on their fur and high metabolism to stay warm. They must eat roughly a quarter of their body weight each day to maintain their energy. Watching a sea otter groom its fur or crack open a meal is to witness intelligence, adaptation, and charm all in one floating, whiskered package. Octopuses are extraordinary creatures, capable of solving problems, escaping enclosures, and even recognizing individual humans. Their intelligence is unusual because it evolved independently from vertebrates, suggesting that complex cognition can arise in many forms. Octopuses have no bones, allowing them to squeeze through impossibly tight spaces. They can change color and texture in an instant, blending seamlessly with their surroundings, or flashing vivid patterns to communicate or warn. Their skin contains specialized cells called chromatophores, which expand or contract to create different colors, and other cells that reflect light or alter texture. Each of their 8 arms contains a cluster of neurons, giving the limbs a degree of independence. An octopus can taste with its arms, manipulate objects with precision, and coordinate movements that would require significant brain power in other animals. They are short-lived, most species surviving only a year or 2, yet in that time they display behaviors that astound researchers. To observe an octopus is to encounter an alien intelligence, familiar yet profoundly different. Among octopuses, one species stands out for its theatrical abilities. The mimic octopus can impersonate other animals with astonishing accuracy. It changes not just its color but its shape and behavior, transforming into lionfish, sea snakes, flatfish, and more. When threatened, it might spread its arms to mimic the venomous spines of a lionfish. If fleeing, it can flatten itself and glide along the seafloor like a sole. This mimicry is not instinctive. The octopus learns by observation, adjusting its performance based on which predator it needs to deceive. Such flexibility requires intelligence, memory, and an understanding of other species' behaviors. The mimic octopus is found in the shallow waters of the Indo-Pacific, often in sandy or muddy environments where its chameleonic skills are most useful. To witness its transformations is to see evolution's creativity on full display. Long before dinosaurs, before fish, before the first creatures crawled onto land, jellyfish drifted through ancient seas. Fossils show they have existed for at least 500 million years, making them one of Earth's oldest multicellular life forms. They have survived every mass extinction, adapting to countless changes in ocean chemistry and climate. Jellyfish have no brain, no heart, no bones. They are mostly water, simple yet resilient. Their bodies are radially symmetrical, with tentacles trailing beneath a bell-shaped dome. Some are tiny, no larger than a pinhead. Others, like the lion's mane jellyfish, can grow tentacles over 30 meters long. Despite their simplicity, jellyfish are effective predators, using stinging cells called nematocysts to capture prey. Their success lies in their minimalism. They need little energy, can tolerate a wide range of conditions, and reproduce prolifically. In a changing ocean, jellyfish populations are booming in many areas, filling ecological niches left empty by overfishing and warming waters. Most organisms age and eventually die, but one species of jellyfish appears to have found a way around mortality. Turritopsis dohoney, often called the immortal jellyfish, can reverse its life cycle. When injured, stressed, or simply old, it can transform back into its juvenile polyp stage, essentially restarting its life. From there, it matures again into an adult, repeating the cycle indefinitely. This process, called transdifferentiation, allows its cells to change type, something rare in the animal kingdom. In theory, an individual immortal jellyfish could live forever, though in practice most are eaten or succumb to disease. Still, the discovery has fascinated scientists studying aging and regeneration. If we could understand how this jellyfish resets its biological clock, it might unlock secrets about longevity and healing in other organisms. The immortal jellyfish reminds us that biology is far stranger and more flexible than we often assume. While sound travels well through water over long distances, the ocean is not uniformly noisy. Certain depths and conditions absorb sound waves, creating pockets of profound silence. In these zones, acoustic energy dissipates quickly, and even loud noises fade into nothingness within a short distance. This can disorient marine animals that rely on echolocation or sound communication. Submarines sometimes use these acoustic shadows to hide, knowing their engines will be difficult to detect. Yet in other parts of the ocean, sound channels form where temperature and pressure align in ways that trap sound waves, allowing them to travel thousands of kilometers with little loss. Whales and other marine mammals may use these channels to communicate across vast distances, their calls bouncing through the ocean like messages in a bottle. The ocean's acoustic landscape is as varied as its physical one, a hidden dimension of the underwater world. For most of history, the ocean was a place of relative quiet, filled only with the sounds of waves, marine life, and geological activity. But in the past century, human activity has transformed the underwater soundscape. Ship engines rumble constantly along major trade routes. Sonar used for navigation and military purposes sends out powerful pulses. Seismic surveys for oil and gas exploration blast the seafloor with intense sound waves. All of this noise interferes with marine animals, particularly those that rely on sound for communication, navigation, and hunting. Whales and dolphins can become disoriented, separated from their pods or unable to find food. Some strandings have been linked to naval sonar exercises. The quieter ocean of the past is fading, replaced by an environment where human sounds dominate. Efforts to reduce ocean noise through quieter ship designs and regulations on sonar use are important steps toward restoring balance. It seems paradoxical, but underwater waterfalls exist. These occur where dense cold water spills over underwater ridges and cascades down into deeper basins. The largest known underwater waterfall is in the Denmark Strait between Greenland and Iceland. Cold, dense water from the Nordic seas meets warmer water from the Irminger Sea, and the cold water, being heavier, plunges downward. This underwater cataract carries more than 100 times the flow of all rivers on Earth combined. It drops over 3.5 kilometers, creating a cascade far larger than any waterfall on land. Though invisible from the surface, these underwater waterfalls play crucial roles in ocean circulation, driving currents that distribute heat, nutrients, and oxygen throughout the ocean. They are geological marvels hidden beneath the waves, reminding us that the familiar rules of the surface world apply differently in the depths. The ocean is never still. Currents flow constantly, driven by wind, temperature differences, and the Earth's rotation. Together, these currents form what scientists call the global conveyor belt, a vast system of circulation that connects all the world's oceans. Warm surface water flows from the tropics toward the poles, where it cools, becomes denser, and sinks. This cold, deep water then flows back toward the equator, slowly rising and warming again. The entire cycle can take 1,000 years to complete. This conveyor belt distributes heat around the planet, moderating climates and making certain regions habitable. It also transports nutrients, supporting marine ecosystems far from where the nutrients originated. Changes to this circulation, caused by melting ice or warming temperatures, could have profound effects on global climate. The ocean's currents are the planet's circulatory system, quietly keeping everything in balance. The ocean is ancient, and within its waters and sediments lie traces of Earth's entire history. Dissolved minerals carry signatures of volcanic eruptions from millions of years ago. Microscopic shells in the sediment record changes in climate and ocean chemistry. Even the water itself contains molecules that have cycled through countless organisms, clouds, and rivers over billions of years. When you swim in the ocean, you are touching water that once fell as rain on dinosaurs, that flowed through ancient rivers, that was locked in ice during the last glaciation. The ocean is a living archive, holding within it the accumulated history of the planet. Scientists study these traces to understand past climates, predict future changes, and piece together the story of life on Earth. Every drop contains memory, a connection to everything that has ever lived. In the coldest parts of the ocean, near the poles, temperatures can drop below the freezing point of normal seawater. Fish living in these waters would freeze solid, if not for a remarkable adaptation. They produce antifreeze proteins in their blood, molecules that prevent ice crystals from forming even at sub-zero temperatures. These proteins bind to tiny ice crystals as they begin to form, stopping them from growing large enough to damage cells. The discovery of antifreeze proteins revolutionized our understanding of how life adapts to extreme environments. It also has practical applications, with scientists exploring uses in preserving organs for transplant and improving frozen food storage. The fish themselves seem unbothered by their icy surroundings, swimming through waters that would kill most other creatures, sustained by chemistry that defies the usual rules of freezing. The polar oceans are harsh environments, but during the short summer months, they transform into some of the most productive waters on Earth. As ice melts and sunlight returns, phytoplankton bloom in enormous numbers, turning the water green with algae. These microscopic plants form the base of a food web that supports krill, fish, seals, whales, and seabirds. Whales migrate thousands of kilometers to reach polar feeding grounds, where they gorge themselves on krill and fish, building up the fat reserves they'll need for the rest of the year. Seabirds nest on cliffs and islands, their colonies numbering in the millions. The explosion of life is intense but brief. As autumn approaches and darkness returns, most animals migrate to warmer waters or enter a state of dormancy. The polar seas remind us that abundance and scarcity often exist side by side, separated only by the changing seasons. Penguins are flightless birds that have become masters of the ocean. Emperor penguins, the largest species, can dive to depths of over 500 meters and hold their breath for more than 20 minutes. Their bodies are streamlined for swimming, with wings that have evolved into powerful flippers. They can reach speeds of up to 30 kilometers per hour underwater, chasing fish and squid with remarkable agility. On land, penguins may appear awkward, waddling across ice on stubby legs, but in the water they are graceful and efficient. Their bones are solid rather than hollow, helping them dive deeper without excess buoyancy. They have high levels of myoglobin in their muscles, allowing them to store oxygen, and they can slow their heart rate during dives, conserving oxygen and extending their time underwater. Watching a penguin swim is to see a bird transformed into something almost fish-like, perfectly adapted to a world beneath the waves. Arctic terns undertake the longest migration of any animal, traveling from the Arctic to the Antarctic and back each year. A round trip of roughly 70,000 kilometers. They experience 2 summers annually, following the seasonal abundance of food in polar seas. These small seabirds spend most of their lives in flight or on the water, touching land only to breed. Over a lifetime, an Arctic tern may fly the equivalent of 3 round trips to the moon. Their navigation is precise, guided by the sun, stars, and Earth's magnetic field. They face storms, predators, and exhaustion, yet return year after year to the same nesting sites. Their journey is a testament to endurance and the drive to seek out the richest feeding grounds. No matter the distance, sea turtles spend most of their lives in the open ocean, traveling thousands of kilometers. But when it comes time to lay eggs, females return to the very beach where they hatched, sometimes decades earlier. How they navigate with such precision remains partially mysterious, though scientists believe they use the Earth's magnetic field as a guide, imprinting on it as hatchlings. The journey back is long and dangerous. Once on the beach, the female digs a nest in the sand, lays her eggs and returns to the sea, leaving the eggs to incubate on their own. Weeks later, the hatchlings emerge and scramble toward the water, a perilous journey across sand where predators wait. Those that survive will spend years in the ocean before returning, continuing a cycle that has repeated for millions of years. Sea turtles embody patience, endurance, and the deep connection between land and sea. In recent decades, the ocean has become polluted with plastic. Bottles, bags, fishing nets, and countless other items break down into smaller and smaller pieces, forming microplastics, fragments less than 5 millimeters across. These particles are now found throughout the ocean, from surface waters to the deepest trenches. Marine animals ingest them, mistaking them for food. Microplastics have been found in the stomachs of fish, seabirds, whales, and even tiny plankton. They accumulate in food webs, concentrating as they move up through predators. The long-term effects are still being studied, but early research suggests they can cause physical harm, release toxic chemicals, and disrupt biological processes. Cleaning up ocean plastic is a monumental challenge, requiring changes in how we produce, use, and dispose of materials. The ocean's health and our own are intertwined, and the plastic we discard does not disappear. It lingers, a persistent reminder of human impact. The Great Pacific Garbage Patch is often imagined as a floating island of trash, but the reality is more insidious. It is a vast area where plastic debris has concentrated, carried by circular ocean currents called gyres. Rather than a solid mass, it's a diffuse soup of microplastics suspended in the water, often invisible from the surface. Ships can sail through it without seeing obvious signs, yet the concentration of plastic particles can be many times higher than normal seawater. This makes it difficult to clean up. Nets and barriers capture only larger pieces, while the microplastics remain. The patch covers an area estimated to be twice the size of Texas, though its exact boundaries are hard to define. Its existence highlights the scale of plastic pollution and the need for solutions that address the source, not just the symptoms. For thousands of years, humans have relied on the ocean for food, but in recent decades, industrial-scale fishing has pushed many species to the brink. Cod, tuna, sharks, and countless others have seen their populations plummet. Modern fishing technology is incredibly efficient, using sonar to locate schools and massive nets to haul in tons of fish at once. Bycatch, the unintended capture of non-target species, kills dolphins, turtles, and seabirds by the millions. The loss of top predators disrupts ocean ecosystems, allowing smaller species to overpopulate and throwing food webs out of balance. Some fisheries have collapsed entirely, leaving communities that depended on them struggling to survive. Sustainable fishing practices, marine protected areas, and stricter regulations offer hope, but recovery will take time. The ocean's abundance is not limitless, and treating it as such has consequences we are only beginning to fully understand. In response to overfishing and habitat destruction, many countries have established marine protected areas, regions where human activity is limited or prohibited. These sanctuaries allow ecosystems to recover, fish populations to rebuild, and biodiversity to flourish. Studies show that protected areas can lead to dramatic increases in fish size and abundance, benefits that often spill over into surrounding waters, supporting nearby fisheries. The largest marine protected area is in the Pacific, covering over 1 million square kilometers. Enforcement can be challenging, especially in remote regions, but technology like satellite monitoring is helping. Protected areas are not just about conservation. They are investments in the future, ensuring that the ocean remains productive and healthy for generations to come. They are proof that when given a chance, nature can heal. The ocean has acted as a buffer against global warming, absorbing more than 90% of the excess heat trapped by greenhouse gases. Without this, the atmosphere would have warmed much faster, and life on land would face even more severe impacts. But the ocean's capacity is not infinite. As it warms, it expands, contributing to rising sea levels. Warmer water holds less dissolved oxygen, creating dead zones where few creatures can survive. It also disrupts currents and weather patterns, leading to more intense storms and unpredictable conditions. Coral reefs, already stressed by pollution and overfishing, bleach and die in warmer water. Fish populations shift toward the poles, altering ecosystems and affecting communities that depend on them. The ocean has protected us, but it is paying a price, and the changes underway will reshape coastlines, climates, and lives. In addition to warming, the ocean is becoming more acidic as it absorbs carbon dioxide from the atmosphere. When CO2 dissolves in seawater, it forms carbonic acid, lowering the pH. This process, called ocean acidification, makes it harder for organisms like corals, shellfish, and plankton to build their calcium carbonate shells and skeletons. In some areas, the water is becoming corrosive, actually dissolving shells. This threatens the base of marine food webs, as many small creatures with shells are critical food sources for larger animals. Oyster farms have already seen failures linked to acidification. Coral reefs, which rely on calcium carbonate to grow, weaken and become more vulnerable to storms and disease. The changes are happening faster than many species can adapt. Ocean acidification is sometimes called climate change's evil twin, a quieter but equally serious threat to marine life. Exploring the deep ocean requires specialized technology. Submarines designed for extreme depths have thick hulls and spherical pressure chambers to withstand the crushing forces. They carry crews of scientists who peer through small viewports, documenting life and geology in places no human has seen before. Remotely operated vehicles, or ROVs, are unmanned robots controlled from the surface via cables. They carry cameras, lights, and robotic arms, allowing researchers to collect samples and conduct experiments without risking human lives. Autonomous underwater vehicles, or AUVs, operate independently, following pre-programmed routes and gathering data over large areas. These tools have revealed the deep ocean's secrets, from hydrothermal vents to new species. Yet, despite these advances, more than 80% of the ocean remains unmapped and unexplored. Every expedition brings new discoveries, reminding us how little we truly know about the planet we call home. In 1960, Jacques Piccard and Don Walsh descended to the bottom of the Challenger Deep in the Bathyscaphe Trieste, the first humans to reach the deepest point on Earth. They spent just 20 minutes on the seafloor before ascending, but their journey proved that life existed even there. Decades later, in 2012, filmmaker James Cameron made a solo dive in a specially designed submersible, spending hours exploring and filming. More recently, others have followed, including Victor Vescovo, who made multiple dives and discovered new species. Each journey reveals more about this extreme environment, but the depths remain largely inaccessible. The technology required is expensive and risky, and only a handful of vehicles can reach such depths. Yet the allure persists. The deepest ocean represents one of the last true frontiers, a place where exploration still feels pioneering. In a few rare locations around the world, shallow bays are filled with bioluminescent plankton that light up when disturbed. These dinoflagellates produce flashes of blue-green light as a defense mechanism, startling predators or attracting larger animals that might eat the predator. When you swim or kayak through these waters at night, every movement creates a trail of sparkling light. Fish leave glowing streaks, hands lifted from the water drip with luminous droplets. The effect is magical, like swimming through liquid stars. These bays require specific conditions to thrive: warm temperatures, minimal water flow, and high concentrations of plankton. Pollution and development threaten many of them, but efforts to protect these bioluminescent habitats are growing. To experience one is to witness one of nature's most enchanting displays, a reminder of the ocean's endless capacity to surprise and delight. Billions of years ago, life began in the ocean. The first cells emerged in warm, chemical-rich waters, possibly near hydrothermal vents or in shallow tidal pools. For most of Earth's history, life existed only in the sea. Photosynthetic bacteria produced oxygen, gradually transforming the atmosphere and making it possible for more complex organisms to evolve. Fish developed, then amphibians that ventured onto land, carrying the ocean within them in the form of blood and cells. Every living thing on Earth, from the tallest trees to the smallest insects, traces its ancestry back to those ancient seas. Even now, the chemistry of our bodies reflects our marine origins. The salt in our blood echoes the ocean's composition. The rhythms of our cells follow patterns established in water. We are, in a sense, the ocean's children, shaped by its chemistry and carrying its legacy in every breath. Waves are one of the ocean's most recognizable features, yet their formation is a process of energy transfer. Wind blowing across the water's surface creates friction, which generates ripples. As the wind continues, these ripples grow into larger waves. The size of a wave depends on three factors: wind speed, the duration the wind blows, and the fetch, the distance over which the wind travels uninterrupted. In the open ocean, waves can travel thousands of kilometers, carrying energy from distant storms. When they reach shallow water near coastlines, they slow down and grow taller, eventually breaking onto beaches. Waves have shaped coastlines for millions of years, carving cliffs, depositing sand, and creating the rhythmic sound we associate with the sea. To watch waves is to see energy made visible, the wind's invisible force turned into motion and sound. Twice a day in most places, the ocean rises and falls in a rhythm as ancient as the moon itself. Tides are caused by the gravitational pull of the moon, and to a lesser extent, the sun. The moon's gravity pulls on the ocean, creating a bulge of water on the side of Earth closest to it. Another bulge forms on the opposite side due to inertial forces. As Earth rotates, these bulges move, creating high and low tides. When the sun and moon align, during new and full moons, their combined pull creates especially high and low tides called spring tides. When they are at right angles, the effect is minimized, producing neap tides. Tides influence marine life, navigation, and human activities along coasts. Intertidal zones, areas covered and uncovered by tides, are among the most dynamic ecosystems, home to creatures that must survive both underwater and exposed to air. Most ocean waves follow predictable patterns, but occasionally a rogue wave appears, towering far above its neighbors. These waves can reach heights of 30 meters or more, walls of water capable of capsizing ships and destroying offshore platforms. For centuries, sailors told stories of such waves, but scientists dismissed them as myths or exaggerations. Then in 1995, a rogue wave struck an oil platform in the North Sea, and instruments recorded its precise measurements. Since then, researchers have confirmed that rogue waves are real, though rare. They form through a combination of factors: waves converging from different directions, strong currents, and unique oceanographic conditions. Predicting them remains difficult, but understanding them is improving. Rogue waves are reminders that the ocean, for all our knowledge, still holds dangers and surprises. Tsunamis are not ordinary waves. They are generated by sudden movements of the seafloor, usually during underwater earthquakes. When tectonic plates shift, they displace massive amounts of water, creating waves that radiate outward in all directions. In the open ocean, tsunamis may be barely noticeable, just a meter high but traveling at speeds of up to 800 kilometers per hour. As they approach shallow coastal waters, they slow down and pile up, growing into towering walls that crash onto land with devastating force. The 2004 Indian Ocean tsunami killed over 200,000 people across multiple countries. The 2011 Japan tsunami triggered a nuclear disaster. Early warning systems have improved, using seismic sensors and ocean buoys to detect tsunamis and issue alerts. But the best defense is education and preparedness, ensuring coastal communities know how to respond when warnings are issued. The seafloor is not static. Along mid-ocean ridges, tectonic plates are slowly pulling apart, and magma rises to fill the gap, creating new crust. This process, called seafloor spreading, has been happening for hundreds of millions of years. As new crust forms at the ridge, older crust is pushed outward, eventually reaching the edges of ocean basins where it sinks back into the mantle at subduction zones. The entire ocean floor is recycled over roughly 200 million years, making it geologically young compared to continents. Evidence of seafloor spreading includes magnetic striping in rocks, patterns created as the Earth's magnetic field reversed over time and was recorded in cooling magma. This discovery in the 1960s helped confirm the theory of plate tectonics, revolutionizing our understanding of how the planet works. The ocean's saltiness comes from minerals dissolved in water over billions of years. Rivers carry tiny amounts of salts eroded from rocks and soil, depositing them into the sea. Over time, these salts accumulate as water evaporates, but the salts remain. The most abundant salt is sodium chloride, common table salt, but seawater also contains magnesium, calcium, potassium, and many other elements. The average salinity is about 35 grams of salt per liter of water, though this varies. The Dead Sea and the Red Sea are much saltier, while areas near river mouths or melting ice are less salty. Salinity affects water density, ocean circulation, and the types of organisms that can survive in different regions. It is one of the ocean's defining characteristics, shaping its chemistry and ecology. The ocean appears blue for a simple reason. Water absorbs colors at different rates. Red, orange, and yellow wavelengths are absorbed first, within the top few meters. Blue light penetrates deepest, scattering and reflecting back to our eyes. This is why shallow tropical waters look turquoise, and deeper waters appear dark blue. In areas with high concentrations of phytoplankton or sediment, the water may look green or brown instead. The selective absorption of light also affects underwater life. Many deep-sea creatures are red, a color that appears black in the blue filtered light of the depths, providing effective camouflage. The ocean's color is not just aesthetic, it is a consequence of physics, a visible expression of how light interacts with water molecules. When we think of oxygen production, we often picture forests and trees, but the ocean is the planet's true lung, producing more than half of the oxygen in the atmosphere. This oxygen comes from phytoplankton, microscopic plants that drift near the surface, using sunlight for photosynthesis. A single type, Prochlorococcus, is so abundant it's estimated to produce 1 in every 5 breaths we take. These tiny organisms form the base of marine food webs and play a critical role in regulating the climate by absorbing carbon dioxide. Without them, life on Earth as we know it would not be possible. Yet they are vulnerable to warming, acidification, and pollution. Protecting phytoplankton means protecting the ocean's ability to sustain life. Both in the water and on land, the deep ocean is cold, with temperatures hovering just above freezing in most places, around 2 to 4 degrees Celsius. Life there has adapted in remarkable ways. Many deep-sea animals have slow metabolisms, conserving energy in an environment where food is scarce and temperatures are low. Their bodies often contain compounds that act as anti-freeze or prevent proteins from becoming rigid in the cold. Some have gelatinous bodies with high water content, which are less affected by temperature changes. Cold water holds more dissolved oxygen than warm water, which is beneficial, but it also means creatures must be efficient with the energy they do consume. The cold is just one of many challenges in the deep, but life has found ways not just to survive, but to thrive. While most fish are cold-blooded, a few species can generate and retain heat, allowing them to stay warmer than the surrounding water. Tunas, for example, have a system of blood vessels that transfers heat from their muscles to their core, keeping their bodies several degrees warmer. This gives them a metabolic advantage, allowing them to swim faster and hunt more effectively. The opa or moonfish goes even further, warming its entire body, making it the first fully warm-blooded fish discovered. These adaptations are rare and energetically expensive, but they allow these fish to exploit ecological niches others cannot, hunting in cold, deep waters where prey is abundant, but most predators are sluggish. Heat, even a few degrees, can be a powerful advantage in the ocean's competitive environment. Beneath the waves lie the remnants of human history. Thousands of ships rest on the seafloor, from ancient wooden vessels to modern steel hulls. Some sank during storms or battles. Others were abandoned or scuttled deliberately. These wrecks are time capsules, preserving artifacts, cargo, and stories from different eras. Archaeologists study them to learn about trade routes, shipbuilding, and daily life aboard ships. Wrecks also become artificial reefs, colonized by corals, sponges, and fish, transforming sites of tragedy into thriving ecosystems. Famous wrecks like the Titanic draw fascination, but countless others remain undiscovered, hidden in the deep. Each is a reminder of the ocean's power and the fragility of human endeavors against it. Despite centuries of exploration, scientists estimate that millions of marine species remain undiscovered. New creatures are found regularly, from tiny crustaceans to fish that glow in colors never seen before. Deep-sea expeditions often return with organisms that defy classification, requiring new categories to describe them. Advances in technology, like deep-sea cameras and genetic sequencing, are accelerating discoveries. Some newly found species challenge our understanding of biology, thriving in conditions we thought impossible. Others are beautiful, bizarre, or both. Each discovery reminds us that the ocean is still largely unknown, a vast frontier where mysteries outnumber answers. The more we explore, the more we realize how much remains to be seen. Everything is connected through the ocean. The water you drink may have once been part of a distant sea. The oxygen you breathe was likely produced by phytoplankton. The climate in your region is shaped by ocean currents. The fish on your plate traveled through complex food webs. The ocean regulates temperature, distributes nutrients, and drives the water cycle. It has shaped human history, enabling trade, migration, and cultural exchange. To understand the ocean is to understand our place on this planet. We are not separate from it. We are part of it, dependent on its health and resilience. Protecting the ocean is not just an environmental issue. It is a matter of survival, of preserving the systems that make life possible. For all we have learned, the deep ocean remains the least explored place on our planet. We have better maps of Mars than of the seafloor. More people have been to space than to the deepest parts of the ocean. Every expedition uncovers something unexpected, whether new species, geological features, or insights into how life adapts to extremes. The deep is a place of wonder and humility, reminding us that Earth still holds frontiers. As technology improves, we will see more, understand more, and perhaps be surprised more. But the ocean's mysteries will never be fully exhausted. There will always be something deeper, something stranger, something waiting in the dark water below. And so, dear listener, our journey through the depths comes to a close. From the sunlit waves to the crushing darkness of the trenches, from glowing jellyfish to ancient whales, we have wandered together through a world both alien and essential. We have glimpsed creatures that create their own light, mountains that dwarf anything on land, and ecosystems thriving where life seems impossible. The ocean reminds us that Earth is vast, mysterious, and endlessly creative. It shows us both fragility and resilience, silence and song, darkness and glowing beauty. Every current carries stories. Every wave holds memory. Every drop connects us to something larger than ourselves. As you lie here, let your breath fall into a slow, easy rhythm, like the gentle rise and fall of tides. Picture yourself floating peacefully on calm water, the sky above, the depths below. Imagine the soft sound of waves lapping at the shore, the coolness of the sea breeze, and the vast, quiet world beneath. See the glow of bioluminescence flickering in the dark. Hear the distant songs of whales echoing through the deep. Feel the slow drift of currents, ancient and patient, carrying you gently into stillness, into rest, into sleep. The ocean has carried countless generations before us, and it will carry countless more. Its story is not finished, and neither is ours. But for now, let the quiet of the deep hold you. Let the rhythm of the waves cradle you. Close your eyes, breathe deeply, and drift into sleep, into stillness, into the vast and timeless embrace of the ocean. Good night.